First of all, thank you all so much for being here and for inviting me to speak. I'm really thrilled to be here and to talk about two topics that are really close to my heart and that I think also are a good fit for this workshop, which are hierarchical methods for task-driven and dynamic scene understanding. Sweet. So I'll take us from the beautiful world of augmented reality back to the ugly world of robotics. Here an example from my former office in Zurich, where what we really want to do is make robots that are useful to people and to society as a whole. And one way to think about this is robots that can interact with their environment. In order to do so, they need to know what is around them. So they first sense the environment with their sensors, quite noisy data. You then build a mental representation, unified model of that scene from the sensing data, typically called perception. And here we specifically care about building scene representations that are useful to do reasoning and planning on the robot. So once we've come up with a course of action that we like, we can ideally execute this on the robot and make the end user happy. So on this talk, I will be focusing on this very bubble of how do we build scene representations that are useful to do reasoning and planning. Also, today, we mostly see robots in these kinds of environments, which although they are complex and things are moving, honestly, usually not that much perception is happening. So where we really see a lot of the impact of autonomous mobile systems is in our homes, in service and care facilities, in everyday scenarios, which look a bit like this possibly. And one reason why I think we don't see robots in our everyday homes as of now is because these scenes are just really, really hard from a perception perspective. There's complex geometry and semantics. Everything is constantly moving and changing. People are rearranging the scene. And there's virtually infinite diversity of things that you might be able to find in these environments. To make things even worse, we do want to run things on real robots, which means we have to use the limited and noisy onboard sensing available. We have limited computation. There's no GPU racks flying around on these robots. Because the scene is so dynamic and we want robots to be interactive, all of these need to run online and in real time. And finally, if we do want to run this around people, also safety and interpretability is a consideration. So today I want to talk about essentially three problems where I focus on two of them of what makes a scene representation useful, how do we handle diverse dynamic environments, and how do we do all of this on a robot. And in our lab, we've actually spent quite a few years thinking about these problems, and I'll start with a bit of a historic perspective of one thing we found is most of these tasks do require essentially a robot to ground symbols in the spatial world. So if we want to execute a task like bring me a cup of coffee in the kitchen, we need to know what is a cup of coffee, what is a kitchen. And traditionally, you could fuse all of these incremental measurements into a 3D, for example, voxel map. We can fuse semantic information into these scene representations, and it doesn't work great. But essentially on the individual voxels, we have all of these labels. But usually what we find is a lot of the labels are duplicated. There is a lot of correlation. It's like actually very hard for a robot to find the things that you care about. So if we can organize this in a hierarchical way, such as a scene graph, we see that only really the relevant concepts are structured from very high level to very low level. And we've been working on how to make this work on a robot, where we really start on the low spatial level with a metric semantic reconstruction, which is sort of what I showed you before. But then we can group these different surface elements into objects and agents. We can further create a representation of the topology of the space or an abstraction of the free space in our places layer. We can further cluster this into rooms, into buildings, into places, cities, and so on and so forth to get these hierarchical abstractions. And it turns out this is really, really efficient for robots to reason and to scale to large-scale environments. We've spent also quite a bit of time to make these things run in real time on a robot here with very limited hardware and sensing capabilities. And you can here see the robot moving around, it fuses the depth and semantic information, and we can build these hierarchical 3D scene graphs in real time on mobile robots. And we can also use the hierarchy to really scale this to large scale spaces, where you can see here in the bottom, loop closure will be detected, and we align all of these things to have one single persistent, globally consistent representation. Now, traditionally, this has been done in a closed set semantics kind of way, where you know a priori what are the symbols you care about. And there's like 10 to 1,000 labels that we can detect. And if you know what these symbols are, that's actually great because it's very clearly defined what are the things you care about. We have these rules for how to get these abstractions, and it works really well. However, a big problem is we have this limited expressiveness of there's many more tasks that we would want to support. And recently, of course, there's been a lot of progress in open set semantics, where we here see an oversegmentation of the scene by the segment anything model. And we can also get feature labels, open set feature labels for all of these different things. And what is great, we have this virtually infinite information about the environment, But the new question arises, how do we actually effectively store and use this in robotics? And here in this project called Clio, we thought about this question where most PhD students in perception at their defense gets asked this very philosophical question of what even is an object or what makes a scene representation useful. And we thought with all of this open set information, it's actually a great time to think about this problem and how do we run this on real robots. So our answer to this question is actually based on a very nice piece of information theory, which is called the information bottleneck, where we essentially try to find, or we're given an input signal X, which could be sensor data from the robot, and we try to find a compressed representation X tilde. In our case, this would be the scene representation, parameterized as a hierarchical 3D scene graph. Now, the answer that you will usually get if you talk to people about what is an object is it depends, and we think this is actually the correct answer to the question, because it depends on what you want to do with it. So we have this extra relevancy variable Y, which could be a task specified in natural language, such as read cracking the coding interview. Now, what the information bottleneck does is it tries to minimize the mutual information between the input and the map. So we want to find a map that is as compact as possible, but also maximizing the mutual information between the map and the task. So we want to find a map that is as useful as possible. And we can actually turn this into a real-time system where we start from the sensor data. We run lightweight foundation models such as SAM and CLIP on these frames. We aggregate them through time and fuse them into what we call object primitives, which is the finest granularity we care about the scene. So the second input to the system is a task list, which we know a priori. And it turns out, was shown before, that there exist greedy clustering algorithms in this information bottleneck that actually combine all of these segments to give us an optimal solution to this information bottleneck problem. So we find from the primitives a combination of primitives into objects, and we can also throw away the irrelevant ones. Now, what is cool about this is we get a set of only the relevant objects in our environment, and it actually generalizes to all sorts of different concepts. So if we have pieces of free space that have clip features, we can also cluster these with the exact same methodology into task-relevant regions. So here we see this system running in real time. It's slightly sped up. We see this list of 20 different tasks that the robot is given. We see this highly cluttered real-world environment with all of the oversegmentation, and only a few really relevant objects pop up, and we are also able to identify meaningful task regions in these hyperlevel abstractions. Now, one thing that I personally really like about this is it also answers the question of what is the right granularity of an object. So if we here scan this environment, and our task is, for example, get us the condiment packets, we get one object over here, which are the condiment packets. But if the same robot sees the same scene with a different task list, for example, get us the hot sauce packets, all of a sudden we find two packets here, because now differentiating between hot sauce and other sauce is really important. What is even cooler is we can run this in real time on this Boston Dynamics Spots robot. So here Spot is being remote controlled, and it looks like we look at all of these objects really carefully. This is because our operator couldn't see what Spot is seeing, and we wanted to make sure we have all of the right sensing data. Clio is running in real time and building this scene graph. And this was the first time we could build these open set hierarchical scene graphs in real time. Previous method used around 6 hours to process a scene of this scale. And once we collected this, while everything is still running, we can switch Spot into fully autonomous mode, and it has all of the information it needs to autonomously complete such things as pick and place operations. So it knows where it can navigate, it knows what a squid toy is, it knows where and what green and blue plastic cones are. So we can do these things autonomously. Now, this is really great. We get all of these task-relevant symbols, where we can finally answer these questions, such as taking the red espresso mug from the cupboard in the kitchen, and we put it in the coffee machine, and we press the go button. We find all of these symbols. This is amazing. But nobody wants to talk to the robot like that, right? What we want to say is, go and make us a coffee. But if you just give coffee to Clip, it usually actually struggles quite a lot to find good things in this scene. So in very recent work, which is actually going to be presented at CVPR, by our collaborator Yoon, maybe he's in the room, make sure you talk to him. He asked the question, can we actually be smarter about this, and we start from the high level task, but then also address the task in a hierarchical fashion. So we can generate, for example, subtasks. In order to make coffee, we need to get a cup, operate the coffee machine, and mix a drink, and then find the task relevant objects. In order to get the cup, we might need a saucer, an espresso cup, and so on and so forth. Now, what is really important is We also need the physical scene grounding. So all of these tasks are pretty useless if we don't actually have saucers and espresso cups in our environments. And we can actually address this in two phases. First, through the automatic scene graph generation, where we again start from the information bottleneck, slightly different notation, but it's the same idea of we want to compress the primitives and retain task relevance. And actually, Yoon showed in his paper that this generalizes to a hierarchical formulation, where we start from the primitives, we are given this hierarchical task decomposition, and we can formulate again from these clip singularities the task relevant of the primitives. And we can also do this in a Markov chain to essentially chain together all of these probabilities of clustering the objects to consider the subtasks and the tasks. And if you do all of your math correct, you actually end up with this very nice formulation for the hierarchical information bottleneck. Now, the next part is how do we actually improve our task hierarchy from this? And we can usually start by asking just a large foundation model, given the high-level task, what are subtasks that we should do? And given this scene hierarchy, we can find the 3D scene graph. Now, usually it's actually quite hard to find good symbols for this. So we can have the other way around where the scene graph says, these are objects that are also around that you haven't used right now. And we can refine our task hierarchy to actually use the things that exist in the real world. And if you do this in a loop, we get essentially this. So we start with the initial question, which is what you get from ChatGPT, of inspect the cleanliness of the utility area. And you find there's actually not that many tasks which can be successfully grounded, and there's not a lot of objects that really support these tasks, such as the floor. But if we iterate on this, we actually find more and more feasible tasks and more objects actually relevant to do these things, and we can create this much more useful scene representation. And what is really cool, we show in the paper that first of all, using this model, we get a better grounding of the predictions, so we can outperform ChatGPT and so on, but also building these kinds of scene graphs, we can find more successful task compositions than if we use other open set scene graph formulations. As mentioned, this is going to be presented by Yoon. Make sure to stop by his poster and ask him all of the really difficult questions about the details of this work. Now, to switch gears a little, I want to spend the second half talking about how to handle diverse and dynamic scenes. And if we want robots that operate in our homes, there's usually a lot of people around, and we get what is called short-term dynamics, meaning people and agents moving in front of the robot, so we need to perform motion segmentation and all of these things. But at the same time, there's also long-term dynamics, which means things changing while the robot is not looking at them, such as these very light changes imparted on the scene, which usually is addressed in an offline change detection setting. But of course, in the real world, a lot of things change behind the robot while it's still running. And these two communities don't talk to each other all that often. So we thought, can we find a unified representation for both these kinds of dynamics? And we termed this very verbosely the spatiotemporal metric semantic slam problem, where we want to find a spatiotemporal representation, so an evolution over the history of the scene that is consistent with respect to space, time, and semantics. We want the representation to have a dense reconstruction and object-level scene understanding, such that it is useful to do reasoning and planning. And finally, we want to do all of this in a simultaneous localization and mapping fashion, meaning it runs on board of the robot and in real time. And it turns out we can actually formalize this as a maximum a posteriori estimation problem, where we want to find the state of all objects and all of the background at all times. So here, every object, OI at time t, has a surface, which can be time varying, so it can be deforming. It has a pose, which can be time varying, so it can be moving, and it has a semantic label or feature. We further want to estimate all of the robot poses, and we want to do this based on measurements of the robot's environment and eco motion. Now, unsurprisingly, it turns out this is a really, really hard optimization problem to solve because we have a large number of variables that grows extremely quickly. Everything is time dependent. And there's this strong coupling between different sources of error. So the short-term dynamics, long-term dynamics, global consistency from pose uncertainty, as well as sensing noise. So what we show in the paper is that by making a fairly lightweight assumption of local consistency, which just means your odometry doesn't jump around and the world doesn't teleport around, things are somewhat continuous, we can actually find this nice decomposition where we introduce a new latent variable y. These are locally consistent fragments of measurements, which is actually the only thing that depends on measurements and only a subset of those. And it turns out if you then optimize spatially over these fragments and then reconsolidate them all into a single temporal representation, solutions to this much, much simpler problem are actually good solutions to the initial problem. And we also integrated this into a system that is based on exactly this factorization, which is called Chronos. And this is what Chronos looks like if you run it on a robot. So here we see a Jackal wheeled robot with a RGBD depth camera. So again, this is robotics, really noisy data, and this is not Gaussian splatting. This is something that runs in real time. But what I want to highlight about this method is really this emphasis on time. So we here see on the Y or the C axis the number of objects believed to be present in the scene as an arbitrary metric. And we have these two time axes of the wall time, capital T elapsed for the robot, and the belief over all previous times, lowercase t. So naturally, the real time axis is on the diagonal, which is the belief about the current time. We can see that as the robot moves around, it observes more objects and the number of objects present increases. Soon, the robot will also observe moving and deformable objects, such as this person, which is correctly detected and represented in purple. And now the robot will go back to its starting position, realize it's in the same place. We'll see how the background and the robot poses are optimized for global consistency. And the robot now also correctly detects that this chair has disappeared while the robot was away. So we see this drop in number of objects present. And we also realize that this cooler over here has newly appeared, so the number of objects present increases again. Now, what is really cool is given all of this data up until capital T time, we can play back the robot's belief over all previous times that it's estimated, sort of what was the background like, where was the robot, where were all of the moving and dynamic objects. And what is really cool is our belief about when these changes occurred actually has changed based on when we last saw them to be present and first noticed them to be absent. And in the same fashion, it's actually really cool if we just care about what was the world like at lowercase t equals 20 seconds, and the robot gathers more data in the future, we can see how the background becomes more complete, it becomes more optimized, and more objects are detected. So we also have this flow of information back through time. In this fashion, we can now for the first time optimize over histories of dense reconstructions on board mobile robots. This is going to be the only very brief table that I show, where essentially we show that this performance is also independent of what the individual objects are. So we tested it on a bunch of different closed and open set objects. We adapted the method based on concept graphs. And what is really cool is whatever you think your objects are, there's very different granularity from big and small objects. Chronos is actually able to handle the long-term changes in the dynamics fairly well in both cases. Now that we are able to get these reconstructions of the background and all of the moving, persistent, and changing objects, we can again use these higher level abstractions, spatially of the scene of what are places, rooms, and buildings. But why stop at space? So we're currently working on finding also temporal abstractions of which parts of the scene are most dynamic, what are predominant dynamics patterns, and how can we essentially capture those in the environment. Now, next to knowing what has all happened in the past, in order for robots to be really effective, we also need to be able to predict what is the future going to be like. And there is one example on object change prediction. We first had to define what are all of the things that can change about objects. So there can be state changes, such as going from a closed to an open state. There can be position changes, such as objects moving around, and we can have instance changes where objects are being added or removed from the scene. And actually turns out, again, these abstractions are super useful. We turn the 3D scene into a scene graph. What are all the objects and their relations? And we can actually train models on this back in the time, for example, graph neural networks that directly perform inference on this object level of how likely are certain things to change. And we can also directly ground this back into the spatial layer of how would the scene look like with these changes. And what we find is this is a really, really hard problem to solve because it is highly, highly multimodal. There's a range of things that are plausible or even possible, but only one of these futures will realize. So the prediction performance is never good, but what we find is we learn a good prior that things like monitors are most likely to be changed, that chairs in front of desks are more likely to move than chairs in the corner of a room, and that small handheld items, for example, are the most likely to move. Now, what I, as a roboticist, find the most exciting part is even if the prediction performance is really bad, it's around 70%, I think, it's still useful to improve task performance. So here a robot is tasked to find all of the changed objects, and we see that using this prior from the network shown in blue, we're actually 66% faster on average in completing this task compared to an optimal coverage task shown in orange. So even a bad prediction can be a good prior. The final bit that I want to show today is we can generalize this to actually much, much more complicated future dynamics predictions, such as in the case of long-term human motion prediction. So here we are given a person, and we've observed part of their path trajectory. Now the question is, where is the person going to go next in the future? And a large part of the body of work in this focuses on prediction horizons of up to 5 seconds, which is amazing for collision avoidance. However, if you care about longer term futures of active interception or active avoidance, all of a sudden, people get really, really complicated nonlinear trajectories that are really hard to estimate. So here our idea is, if we knew about the environment and its objects, that should be useful to tell us where a person is likely to end up. And we actually designed a system where we start from the trajectory, we have some observation of the past actions of the person, and we're given the hierarchical 3D scene graph of the scene. So here the robot has mapped your home, and now we just want to perform inference. And we can actually generalize the standard intent prediction, where we can reason on a very high level about what are things the person might want to do, and we then ground it back into the physical space for trajectory prediction. What I get out of this is actually a really nice 4D distribution over future positions of the person, and we can even sample from this distribution to get discrete trajectories. To give an intuition on how this works, we operate on this level of the scene graph where the person started. We see all of the different things that the person's done before. Maybe they shut down their PC, they stood up from the chair. And now we can ask a large language model that is conditioned on the scene graph, what are things the person might want to do next? And we can actually do recursive prompting to build a multi-hypothesis tree of possible interaction sequences that people might want to do in this environment. And what is really cool is, because we have this places layer, we can actually spatially ground all of these interactions back into trajectories. And the final bit we need to solve is, how does time come into an equation? And what is really cool is, if we define transition probabilities, for example, what is the probability of different walking speeds? What is the probability of interacting with an object for a given amount of time? Or what is the probability of branching in this multi-hypothesis trajectory? These are all things we can get from data, or in our case, you can actually ask ChatGPT for it and we'll give you good estimates. Then we can actually use this to define a probability distribution using a continuous time Markov chain equation. So essentially all of these probabilities give us a transition matrix, and the solution to this equation is known, and it turns out, because it's a tree, Q is trigonal, and is actually very, very fast to compute. So figuratively, we start with all of the probability mass at the origin, and then we essentially can model this flow of probability mass through the spatial tree of multi-hypothesis trajectories. And this is what it looks like if you run it. You really see it's nice multimodal. There's different places the person might want to go. And the probability mass accumulates in areas where people are most likely to be found or interact with objects for a long time. Now, if we look also at quantitative results, we can here see the negative log likelihood, meaning the lower the number, the more probable is the true trajectory under our distribution. So the lower, the better. And we find that our method actually generalizes to much, much longer time horizons than existing methods that were even trained on the relevant data, but also achieves much higher prediction performance. And something that's really cool about this, say, more classical method of building a probability distribution is we can compute the steady state of this distribution, so we know when the prediction or when the observations of the past trajectory are no longer informative for our prediction, which actually happens after a few minutes. And we also realize that it never gets as bad as random, because the steady state distribution has this common sense knowledge from the LLM imbued in it. So to wrap up and summarize, today I hope I could convince you that hierarchical representations can be really, really useful to do effective, large scale and long horizon planning and reasoning on robots. We've seen that these scene graphs are really, really useful to not only find the abstraction into these higher level symbols, but these symbols interface really, really well with reasoning models or large language models. And the other thing that is really important is the return ticket back from the high level to the physical and spatial grounding, with which we can actually predict very nice distributions and start more looking into temporal modeling, which I think is also a fairly underexplored area. So we hope to see more contributions from you there. As a final bit, we've started exploring in the lab this new direction of essentially task-relevant scene representations. And I hope I could convince you that this is something interesting to look into that can give us very compact and still effective representations if the robot knows what it has to do ahead of time. A big thank you to all of the collaborators, and primarily the students that have been doing a lot of the heavy lifting on this work, all of our sponsors, many more collaborators that unfortunately I couldn't list. And all of the works that are presented today are available open source. Make sure to check this out if you think it's useful to you. You can run it. I'll be happy to take questions now. feel free to shoot me an email later if I don't have time. Thank you so much.
Do we have any questions? I think we have time for one question.
Really nice presentation, thank you. A quick question, how much of this work do you think can be applicable to outdoor space, like the kind of perception prediction of self-driving cars?
Excellent question. So I did focus today on the indoor case because there's only so much time we can spend at these presentations. But actually, we do have a lot of work generalizing this to outdoor scenes where some of the questions become a bit more philosophical on the hierarchy might be less well defined, right? Like indoors, because it's human made, there's a lot of concepts that are easy to abstract. It is also clear what is the ground truth. Outdoors, the abstractions can be a bit harder to define of what is even a meaningful abstraction. But there's different ways to estimate this and to get different hierarchies also for outdoor spaces.
All right, let's thank the speaker again.
Thank you.